here. So without further delay, let me give a very brief introduction of Shubham. Thank you, Shubham, for accepting our invite to share your knowledge about the post-processing techniques using Python. So Shubham Goswami is a PhD scholar in the University of Alberta. I think he is a senior PhD scholar going to finish his thesis very soon. And he is very much active in sharing the OpenFOAM knowledge through his Medium articles. And so I invited him to share his knowledge on the post-processing techniques of OpenFOAM data using Python, which came up in discussion of yesterday's that how we can post-process data efficiently. So without the further delay, I request Shubham to start with the training session.
Sure. Thanks, Dr. Bose, for inviting me. So today I'll present a brief workshop on advanced techniques for analyzing OpenFOAM data using Python. Just to give you a background of where this workflow comes from. So since I started learning OpenFOAM and started like using OpenFOAM about 8 years ago, I was trying to look for methods to basically tag OpenFOAM with Python because that was the programming language that I was learning at that point. So I wanted to basically develop a workflow kind of so that I can basically efficiently analyze, like my simulate things in OpenFOAM and just visualize and analyze it in Python. So the idea behind this technique was basically to bring together a CFD powerhouse, which is OpenFOAM, and data analysis powerhouse, which is Python. So Python offers these powerful built-in modules, such as like NumPy, SciPy, Matplotlib, FluidFlow, and PyVista. It is also interactable and portable in the way that you can explore things by basically running those block scripts in Jupyter. And OpenFOAM, apart from it being this wonderful CFD powerhouse, it offers two amazing features that I absolutely like. So first, it has a lot of function objects. So it has a lot of built-in post-processing functionality through function objects. And second, it has an amazing command line functionality that I basically use on a daily basis. So where this workflow comes from, like it comes from certain constraints that I set for myself when I started my research. First and foremost, I wanted to basically work on data that was stored on these high performance computing clusters. So the idea there was that I set up my case locally, upload it to an HPC cluster, do all my pre-processing step till decomposition, and then run my case. And when my OpenFOAM simulation ended, that's where my problem started. So first of all, locally, I didn't have enough power to store it or even analyze that data. So I wanted to come up with a easy way at that point where I can basically work with HPC stored data directly in terms of basically exploring data and visualizing data fast, like visualizing and analyzing the data really fast. Uh, in terms of visualization, what I aimed for is not to use ParaView, Visit, or TechPlot. I wanted a more simpler way. Now, all of these three tools, they're really vast in terms of their functionality, but I wanted to get something simple. So for me, Matplotlib was the simplest plotting tool that I use. So I wanted to do something with Python at that point. And moreover, I didn't want to change or add anything to the source code anywhere. So I wanted to create a smooth simulation to analysis workflow. And basically using all these constraints, I came up with this workflow that has been working for me like since last 8 years now. So just going into a bit of background before starting the training, there have been a lot of projects that have brought together OpenFOAM and Python previously. But how this workflow differs from others is that, first of all, it's only a post-processing implementation. So I'm not changing anything in the source code, nor in Python or OpenFOAM. I'm not adding anything in the OpenFOAM uh, header or C file so that I can tag, like I can run Python codes in there. All I'm doing is running my simulation on OpenFOAM, extracting data from there, and trying to visualize and analyze that data in Python. So in this workshop, I'm going to follow two examples. First, a simple flow over a square cylinder at Reynolds number of 100. And second, a case of two side-by-side square cylinders with a gap between them. These cases are run on OpenFOAM. They are 2D incompressible laminar and transient simulations run using PimpleFOAM. Uh, I've run these cases till they're fully developed and achieved a periodic vortex shading. I chose these two cases specifically because I wanted to show something that I can take under like 100,000 cells, which is, I think, big enough to run on any computer, right? So these are the deliverables that the things that I'll show you in this workshop. Let me quickly just go back to this. If you can still see my screen, I've set up a GitHub repository and I'll just share the location of that repository in the chat box. Do that quickly. It's there. So this repository basically contains all the data that's required for this workshop. So if you want to access these files, uh, copy the link that I've sent you and just git clone or download that repository in your local working space and basically just place it somewhere in your working directory that's easy for you to access. In my case, I've just placed those cases uh, at a location, for example, in a place in a folder called workshop. Uh, Now at this point, first let's begin setting up Python. So I've added a requirements text file here in this GitHub repository, which basically includes all the things, like all the Python modules that are necessary to basically recreate these post-processing steps that I'm going to show you. So if you have done Python before, it's simple enough to uh, like load all those modules. If not, like if you don't remember the commands or the functions, I've provided them here. So all you need to do is navigate to, for example, my workspace, and I'll do pip install -r requirements.txt. This file, as I said, contains all the required modules. When you type just enter, and it should go through the installation really fast. In my case, it doesn't need to go through an installation because I've already done that. But in your case, it may take a couple of minutes. So just wait for that to finish. So there are two ways to basically install those dependencies in Python. First, using pip install. Second, using Python pip install. The difference there being that sometimes if you have a lot of different versions of Python, then you can install those requirements in a specific version, whichever one that you would want. So that can be done with additional flags there, but for more general use case, I've just put this command here. Uh, at this point, I'm also assuming that you have a active working OpenFOAM environment in your PC. So in my case, all I need to do is start my OpenFOAM environment using OF 2312. Uh, it like just assuming that you have a working OpenFOAM and Python environment in your PC. So let's go through the deliverables. Uh, if you just check the cases that are available on this GitHub directory, uh, the first case that we are going to use that I'm going to show you is the case of two cylinders at Reynolds number of 75 just 75. We have a post-processing folder with probes and forces. So what I did was I included a couple of probes and I wanted to extract forces on both my cylinders at that point. If you just want to visualize what that two cylinder flow would look like, it would basically look something like this. The animation at bottom right here. So intuitively, I can see that both the cylinders have this amazing vortex shedding behind them, and I don't see any impingement of any of those shedding on each other. So the flow is more or less periodic, steady. Let's go back to the deliverables again. So the the idea behind this workshop and like my workflow is to basically extract the information available in this folder, this post-processing folder, into Python and analyze it. So in lieu of that, we're going to extract and plot the velocity and pressure probes along pressure values along different probes that are given in this file. We're also going to extract and plot force coefficient data given here through force 1 and force 2. Since I will have those two, I will also go on to compute a FFT to get a power spectral density and just check my dominant frequency of the flow using the pressure and force probe data. Further, I will extract and plot data along multiple lines from a simulation. So just to give you a perspective of that, for that part, for that deliverable, I'm going to use the case of a single square cylinder at a Reynolds number of 100. And I'm going to extract information along this center line behind the cylinder and at two lines at 4 and 8D downstream of the cylinder. And I'm going to plot it and just visualize it here. And finally, I'll extract some 2D slice data and visualize it to get a view of the flow field. Uh, After all of that, if you get some time, I can cover some advanced analysis options such as POD, DMD, and animations that I usually write about in my blogs. So if you're following along, I have added a workshop notebook in this repository here that you can download and follow along with me. So let me just open up those cases here, and this is that IPython notebook here. So I'll begin with just loading the necessary modules. First of all, I'll just load the modules that are needed for me: Matplotlib, NumPy, Pandas, and SciPy. OS is a module that I usually load just in case I want to read any files from the system. Following that, define your paths to where your case is. So if I'm going to use the case of two cylinders at Reynolds number of 75, I'll define the path to that specific case. And I also define a path where I want to save all my files. So in this case, I'll define a folder called figures where I would save all the things that I'll generate here. So I'll begin with my first point. So I want to extract and plot velocity and pressure along different probe points. So for that, I'll use this Python package called FluidFOAM. FluidFOAM project started about in 2020. Before that, I used to use a really coarse version of FluidFOAM, which was called OWL, I think. Which so this package specifically is a package that's designed for OpenFOAM to read different OpenFOAM classes straight from the OpenFOAM into Python. So for that, I'll import my FluidFOAM module, and first there is a command available called FluidFOAM read probes. All you need to do there is define the paths to your probe data, like your post-processing folder, path here to your probes. I want to check my latest time step. So I don't want the startup wake effects. I just want to analyze the data after my fully developed flow. I'll do that here. There are other options available called merge time, which includes both of these folders. For me, the latest time option just includes the folder that's my latest. So using this, I can extract my velocity and pressure probes. So, oh, didn't define the path. Let's go back. Yeah, this works now. So with that, the probe data is extracted. Uh, with this command, we basically give it to three different variables. The first variable defines the location of that probe. The second variable defines the time, and the third variable defines the velocity, like the values of velocity and pressure at that probe location itself. So you can visualize where those probe locations are. So this locations is basically a huge NumPy array. And with velocity, that probe location is indexed in a way that the first variable is all your velocities. Second variable is the location of your probe. So it's just the index location of your probe. So in this case, number 4 would mean this one. So I'm looking at velocity and pressure at this specific probe location. So when I just execute these two print variables, all I get is first my velocities and then just the shape of my time and the velocity probes. Same thing with pressure. Uh, since pressure is a scalar, my third index will be 0. In case of velocity, my third index can be 0, 1, and 2, since we have velocity x, y, and z. So with pressure, when I do that, I just get pressure values. And with those things extracted, you can basically go on and plot it using like any simple plotting routines in Matplotlib. So here what I'm doing is I'm plotting the trends of velocity at that specific probe location, and I'm also trying to compute and plot my mean velocity there. It doesn't really mean a lot at this point. Like there is not much significance of that mean velocity at a probe location, but it's just handy that you can do that in Python. You can visualize that in this way. Same thing with pressure. I'll do that and I'll see the trends of pressure, both unsteady and mean flow features. Further, I'll go on to extract the forces. So there is a similar functionality in fluid form called read forces, similar to read probes, which basically indexes these folders, force 1 and force 2, and all it does is indexes this dat file for us. So since I have two different cylinders here, I'll define two force variables, force 1 and force 2, and I'm pointing to two different force folders there. So when I execute those, everything's worked fine, means that it's worked okay. I'll see that the force is a NumPy array. I'll pass on this force variable to a pandas data frame so that I can basically just structure my data and give each column their specific index variables. Like if you want to know where this comes from, it comes from your this coefficients.dat file. So if you just open it up quickly, you can see that the first column is time, then drag, then front and rear drag, all those things. So all I do is I write a reduced version of that here and just pass it on to uh, those variables there. Uh, and when I just display that data frame, it would show up like this. So I would have my time, drag, side force, lift, all those things there. And then you can just simply plot it using common plotting routines. So Here I've passed on a couple of variables, like basically plotting my mean force, like mean drag and mean lift uh, for those cylinders. And I get a value of my mean variable there. And I also see the trend of the unsteady drag that's acting, the unsteady drag force that's acting on the cylinders there. So once I have that information, it's really easy to validate it using your whatever way you want to validate it. Here I'm since mimicking the case of March 2017. I've achieved less than 1% difference, so I can call it validated. Same way I can plot the drag for the other cylinder. I can see that the trends are same. The mean drag coefficient is more or less the same. Uh, so in my case, this specific case is refined enough. Uh, Stage 3 is computing FFT. So since I have these drag and velocity signals available to me, I can just pass it on to a simple FFT routine and plot the power spectral density. So when I do it for the velocity, I get this plot with my dominant shedding frequency at 0.15. And I also see a couple of harmonics there. Uh, when I do the same thing for the lift coefficient, I just get one dominant harmonic while my dominant frequency remains more or less the same. And again, I can use that information for validation with that paper that I'm referring to. So here I can again achieve less than 1% deviation. From here on, we are going to use more of OpenFOAM. So the next step is extracting and plotting data along multiple lines from your simulation. So for this, I would go on to my case, which is this one, and I'll just generate a file called multiple lines. This is a function object that's readily available in OpenFOAM. I'll just put information for what lines I want to extract at what different locations. So as I showed before, I'll extract a line along center line and two locations at 4 and 8D away from my prism. And I want to extract velocity, mean pressure, and my Reynolds stresses. So to run this, I'll just go on, open it up in a terminal, and then it's just a case of simply running a post-processing command line function, like function of OpenFOAM. So post-process on multiple lines. When I do that, I let it run, and those lines will be extracted here. So if I go back to my case, I check this post-processing folder, and I'll see that I have multiple lines folder. And I just want to check my latest time. So I see I have 3 different lines. Uh, these are CSV files, which are easy to read in Python. So all I need to do is define my path variables, extract those CSV file locations and their names, extract those lines using pandas, and you can see that I can extract that CSV file here. And then all it remains is to just plot it. And I can see the trend of my mean centerline velocity as well as deficit of velocity, like deficit of time average velocity at different locations downstream. So this is a step of data exploration. So I'm still exploring data from that OpenFOAM simulation using just lines and using quantitative visualizations. The next step is actually doing a bit of qualitative visualization. So I'm going to utilize the surfaces function object. And before that, I'll just run a post-processing utility for vorticity to extract vorticity. In these cases, I've already done that. So I'll extract vorticity for all the available time steps, and then using the surfaces function object, I'll just I'll extract a 2D slice at the center plane at Z0 of my case to just visualize the field, the flow field at that specific location. And then you can simply run post process surfaces. When I do that, it will extract the surface information in a VTP file. And if I go back to my post-processing folder, I'll see the surface information here. And this file basically contains the field data. Let me just check time. I'm at 24 minutes. I'll quickly try to conclude. So to work with a VTK file, I'm going to use PyVista. This is another powerful module in Python that is designed specifically to work with VTK, Visualization Toolkit, where you can read data from a VTK file. So go on and import the PyVista module. I will specify the location, the path to my surfaces folder, and then check my files, that VTP file that's available there, which is this one. And then I can follow the routines available in PyVista to basically just extract data from there. I can see that I have velocity, pressure, and vorticity. And just extract vorticity on velocity here. And I'll just plot that using simple matplotlib routine, and I can see the whole flow field here. This covers the fundamentals of this workflow. Now I'll show you in extension what this workflow can be used for. So if you can extract the field information from one time step, you can actually do that over multiple time steps and stack it in this X, which is a snapshot matrix, which is like a long, skinny, thin and skinny, tall matrix. And once you have that matrix, you can perform proper orthogonal decomposition. It's just a matter of using matrix operations like in Python, and you can do the modal decomposition as such. You can also do dynamic mode decomposition using that data, and with enough snapshots, it would give you enough versatility for TOD and DMD both. I've also used this specific workflow to perform bispectral mode decomposition and spectral proper orthogonal decomposition also. So this workflow just works for me. I'm sharing it with everyone through my blogs so that more people can use it. That what motivated this was that I have struggled a lot with Python and OpenFOAM, and this is a way for me to basically help other researchers not struggle too much. With that, I will conclude my training. I think I'm exactly at 27 minutes. I'm a bit over time. If you have any questions, please feel free to ask me, or I have my information available there. You can even email me if you have any more questions. Thank you.
So I think we have 2 minutes to take a quick question. Some people have raised your hand, but not now. So I think actually in the chat box, they wanted some of the codes which you have already provided through the GitHub link. So you can get the code, just do the git pull and you will get the whole repository. If any of you have a quick question to ask, please raise your hand. If not, please, as I said, please keep your queries posted in the chat box and the speakers will try to actually. Okay, there is one question. Can we model transient phenomena? How difficult it is? I didn't get the question properly, but Shubham, do you want to comment on that?
If I understand, like, so trying to understand. So when you say model a transient phenomenon, uh, as I said before, like I'm doing analysis in OpenFOAM. So all the modeling is happening in OpenFOAM. Python is only used for data extraction and post-processing. But if I can understand that question in another way is I can visualize things, like I can visualize the transient phenomenon using this workflow. So sure, that is possible. So as I showed with POD and DMD data, if you have enough time steps, you can extract that information, and it's only a matter of visualization. Does that answer your question? Sorry, I can't hear you.
Thanks, Shubham. So basically, I think if there are any other questions, please keep an eye for some time in the chat box, and I request you to answer them in the chat
Sure.
box.
All right. Thanks, everyone.
Right. So, Soris, can you please try to turn on your speaker and video?
Sir, can you hear me?
Yes, we can hear you perfectly. Uh, So our next speaker is actually from IIT Kharagpur, Mr. Sourish Singha, and he will speak on customizing standard OpenFOAM solvers for enhanced research capabilities and precise outputs. Can you share it, please?
Sir, I'm not able to share. So can you just let me share my screen?
Yeah, we are trying to make you the presenter. Now you are a presenter. You should be able to. Yes, we can see your screen. Please make it full screen in presenter mode and start your presentation.
Okay.
All right. I request you to be on time, otherwise all the others will be delayed.
Sure, sure.
Yes. Okay.
Okay.
All right.
So, dear all, my today's topic is customizing standard OpenFOAM solvers for enhanced research capabilities and precise outputs. So, the reason we customize OpenFOAM solvers is basically we have some standard solvers available in OpenFOAM dictionaries, but then you need some solvers to include some different type of algorithm. So if you try to include it, you have to create a custom solver, like your own solver. So this solver will be customized. That means that is not that will take the standard solvers and that will create a new solver for based on your requirements. So for this presentation, I'll discuss about a Eulerian Lagrangian solver. So basically, as you know, that fluid we solve as a Eulerian method, and solid, if you have some particles, we solve it in a Lagrangian method. And here we'll actually add these two that and make a new Eulerian Lagrangian solver. So we'll take a Pimple form, which is already available in the OpenFOAM standard dictionary, and then we'll take the also a source code from the Lagrangian particle tracking. So first we'll set up the working environment. So first we'll find where the OpenFOAM 2012 version is. So then you can easily write like dollar w make project dir. You'll find where your OpenFOAM installation directory. Over there you will go to the etc folder, or you can make a run folder also. I'll show you. So there you create a tutorial folder with the mkdir command. That thing you can do it yourself, and then you can create another directory within that tutorial solver directory. So first we will copy our source code from the available OpenFOAM dictionaries. So we'll take the Pimple form solver that is available within the application folder. Within that you have solver directory and incompressible directory. Inside it you will find the Pimple form. Then you copy that particular Pimple form folder to that your new solver which you are trying to customize. So over there, first rename it as a Pimple. I have written at Pimple EL form. You can write anything. You can write your name also, Pimple, your own name form, something like that. And then you after renaming, what you do that inside that you will find that pimplefoam.c, that is a source code file. Then you rename the source code file also. After that, you will find some other solvers inside that pimple foam. So first you delete those things. You don't need that. After that, you add a Lagrangian capabilities because you are to couple the Eulerian and Lagrangian solvers. So then you have to copy the Lagrangian from the intermediate folder. We will find within the SRC folder in the OpenFOAM, and then you copy it and paste it over there. So after that, you'll find a file called createfields.h. So I can show you. It is something like, see, I have made a this by my own name. You can put anything. That's why I just put my name. So within that, you will, after copying pimple form, you'll get all these files and this make folder. And from intermediate, you will copy it from the Lagrangian. So this part is a Lagrangian and this part is Eulerian. So going back to my presentation. So createfields.h is basically where it reads the fields like velocity fields, pressure fields, turbulence quantities, and it initialize also. So it includes all the definition of necessary fields that we required. So first you open this createfields.h and you will find that it is already it is reading velocity and pressure for pimple algorithm. Now you have to include the Lagrangian capabilities within it. So what you do, first you put a class called IO dictionary and you name the class as transport properties. And within that, you in IO input output object class, you just name it just a transport properties. And the way it is located inside the constant folder. In the constant folder, the transport properties file is located. And then you create a mesh object, which is basically where the field is defined on. Then you put a flag that it must read if we modify it, otherwise it won't read, it will take the initial value, or you don't need to write it also in the disk. So then we'll find another class name, which is basically row infinity value. So row inf we write here. So row inf we name the class and then we put a dimension of it, and we'll find it in the laminar transport model. So we have to calculate the inverse row infinity, because when you see the momentum equation from the conservative way you represent the momentum equation, from that when you represent it in a non-conservative way, you divide by the row. So then we have to find the 1 by row value, and for that you take the 1 by row value as 1 by the row infinity value. So these things I have clarified here. After that, you calculate you start reading what is row infinity. So row infinity is basically, it will be row when it is incompressible row, the density, and row infinity both are same for the incompressible flows. But for the compressible flow, row would be different because it is compressible. The row is changing with the time. So it will take the time name also, and also it is the mesh is an object where the field is defined. So the flag is like it will not read it and it will auto write it. So after that, it will like take this value, and then we define what is the dynamic viscosity. So within that OpenFOAM case folder, we always define that the kinematic viscosity. We don't define the dynamic viscosity. So it will take the kinematic viscosity and it will multiply the row infinity value, and it will using that laminar transport model, and it will find the dynamic viscosity value. So then we initialize the particle cloud. So for particle cloud initialization, first we put an argument that either you get the value of the cloud name. Cloud name is a class name, and then otherwise it will take the default name like kinematic cloud. Either you change, you get the new value, or it will take the default value. Then it's an output stream, as you can see info. After that, we name the class as a kinematic cloud, where it will taking the values of the velocity, dynamic viscosity, gravity, density, and all these information from the particle cloud. So these things I have described here. So after that, you actually customize the source code of the pimple foam. So you open that pimple foam, and then you add this line called basic kinematic colliding cloud .h. So I'll show you. It will be better to understand. So you can see like this is my create fields.h. Here I have add after this include create MRF, this multiple reference frame.h. After that, you add those lines basically. Then it will be coupled. It will take the Lagrangian capabilities inside it. So I have already discussed those things. You just need to write it over there. So going back to my presentation, and for the pimple foam source code, you have to add this basic kinematic colliding cloud, which is, if I show, this is my the source code. And there you have to add this line over here, basic kinematic colliding cloud, which is basically the kinematic clouds like particle clouds, like all the particles we call it cloud, and they're colliding, they're hitting each other. So you add this line here, and after that, um, in the next, you also add this read gravitational acceleration dot h, because in pimple foam, when you copy it, the pimple foam source code, you won't find that it read the gravitational acceleration, but you need a gravitational acceleration for that. So this is the two things you need to add. And apart from it, when you let me show you this part. This is the code you will already get in the pimple foam, where it basically opens a pimple loop, and inside that, it first, after first iteration, it check the mesh is moving or not. With outer characters, it fix the mesh, and then it update the mesh with the dynamic mesh control. If you are using the MRF, like multiple reference frame, if something is rotating, then it will update. If it is not rotating, it will not take. So you then correct the phi value, which is the flux value, it will correct. And after that, you solved explicitly that the flux and the velocity, and then you include the ucation.h. Now this is a header file. This is this is the directive preprocessor directive header file, where it actually calculates the differentiate the momentum equation, and it includes the header file over there. So after that, it's correct the pimple loop, and it will take the P equation from it, the pressure correction equation, and also the turbulent correction it will take from the pimple loop. And then after that, you need to add this part, where basically this one, where you add the kinematic cloud over there. And with time, you evolve the kinematic cloud, you add new values to the kinematic cloud, because your particles are moving, and this velocity positions also changing. So kinematic cloud, this is basically a source term, and the velocity we are actually taking over here, and we actually calculate the dimensions vector, which is basically the source term by the dimension volume. Then the primitive field would be minus of the source term by the mesh volume, and then we write it, that particular part. So then after that, we customize the U equation.h. In normally, if you see in pimple foam, in U equation, you won't find the source term for the Lagrangian capabilities. So here you can see is a temporary object file, where you create a temporary U equation. And this is the finite volume method you solve with DDT of U, is a temporal term. You are basically solving it. After that, you solve the phi and U term. This is also explicitly implicitly you are solving these two. After that, you like DDT of you just derivative of U you will find for the multiple reference frame. It is, if nothing is rotating, then it will be 0. Then you include the turbulence part, where you calculate the divergence of deviatic stress tensor. And then within FV options, if you user defined, if you have any source term, you add it. And then this last part you have to add, because it is take the source term for the particles, the force terms it will take. So I have discussed these things. So the final customization is like, you go to the make folder in files. There you, after compilation, it will be saved over there. Like this is the after compilation, this library would be saved over there. And you have to go within that the intermediate folder. Within that, you have to include some header files. These are the header files. And you have to include some libraries also, because before compilation, you need those libraries and you need those header files. Without that, it won't be compiled. So then you compiled it. After compilation, it will save the executable file in the this is an OpenFOAM directory working environment, foam user app bin. Over there, it will save as a pimple EL form. You can save by your name also. And the source code will be pasted over just above that. So then you just write a wmake all, you'll get your new solver. So I can show you. This is my new solver. I put my own name. You can do anything. This is a new solver where it uses Pimple algorithm and it solves the Lagrangian capabilities also add. And I want to show you one of my results. So this is one of my results. So in one I have used Udance and the another one I have used Alias. I think I have finished within time. Thank you.
Thanks, Sourish. It was very insightful talk, and it's a very complete tutorial of how to compile a new solver. So I think it was useful to the users. And again, as I said, for the interest of time, if you have any questions, please write them down in the chat box, and Sourish will try to answer them. So I thank the speaker again then, and we go ahead with our next speaker. Um, and the talk is actually by Mr. Abhishek Sharma from IIT Kharagpur. And he will be talking on particle-laden turbulence, OpenFOAM solver, and TKE utility. So Abhishek, can you unmute yourself and switch on the camera?
Yes, sir. I've done that.
Okay, we can actually see you and hear you. So please share your screen and go ahead with the presentation.
Yes, thank you for the opportunity. Is my screen visible?
Yes, we can see your presentation.
Okay, thank you for the opportunity. Very good afternoon, everyone. Today, I'm going to give a talk on particle-laden turbulence with the perspectives on OpenFOAM solver and TKE, turbulent kinetic energy utility. So this is the outline of my talk. I'll begin with the introduction, followed by how to customize an Eulerian Lagrangian solver in OpenFOAM. Then a new boundary condition for turbulence, followed by TKE budget calculation, the equation which is utilized for TKE calculation, followed by its validation, model validation, and some results of the model. So I'll begin with the introduction. So why do we need particle simulations with OpenFOAM? So OpenFOAM is a free and open source software in which customization and unlimited parallelization is possible. So we can customize all the codes relatively easily, and running it in parallel environment is very easy. OpenFOAM is constantly under development with a continuous growing community uh, like academic research and R&D companies. OpenFOAM already includes solvers for any application of particle-laden flows. Example, process engineering, mechanical engineering, civil engineering, physics, etc. So how do we implement Lagrangian particle tracking in OpenFOAM? Solvers for particle-laden flow are already implemented, in which, for example, this DPM foam is there, which is a transient solver for coupled transport of single kinematic particle cloud, including the effect of volume fraction of particles on the continuous phase. And uncoupled kinematic parcel foam, it is another solver, which is a transient solver for passive transport of single kinematic particle cloud. Then comes one of the example is reacting parcel film foam, which is a transient solver for compressible turbulent flow with a reacting multiphase particle cloud and surface film modeling. Then comes a spray foam, which is a transient solver for compressible turbulent flow with a spray particle cloud. So if proper solver is not available corresponding to our needs, we can customize one of the available, taking help from one of these solvers. So I'll show how to customize the Eulerian Lagrangian solver in OpenFOAM. So suppose we have an incompressible flow, incompressible transient flow in which turbulence is inherently present, and the flow is of Newtonian fluid. And what solver should we use for this type of system? So OpenFOAM gives us Pimple Foam, that is a pressure-based solver designed for transient simulation of incompressible flow. It handles laminar and turbulent single-phase flows under isothermal conditions, accommodating both Newtonian and non-Newtonian fluids. So this is the directory snapshot of pimple foam solver, in which correct phi.h is a header file which consists of flux correction functions to ensure continuity. The create fields.h file, it reads the critical fields and initializes them. The pimplefoam.c file is a transient solver for compressible turbulent flow of Newtonian or non-Newtonian fluids. And the p equation.h and u equation.h files are consisting of definitions of the Pimple algorithm. So Pimple algorithm is nothing but it extracts the positives of simple algorithm and piso algorithm, combines them into two, and it follows this particular algorithm. So this algorithm definitions are present in p equation.h and u equation.h. We choose this solver as the basis of Eulerian-Lagrangian solver. Okay. So to create the Lagrangian aspect of, to include the Lagrangian aspect of the OpenFOAM, what we do is we copy the Lagrangian library intermediate from OpenFOAM v2012 that includes the submodels for particle forces, particle collisions, injection, and dispersion models. So all these are defined in the intermediate library. Then we copy that intermediate library and paste it in the PimpleFOAM solver, PimpleFOAM directory. Next, we open the create fields.h file and add the following lines after include create mrf.h to create and read fluid density from the transport properties and calculate the inverse fluid density. Next, we create the volume scalar field for fluid density and the dynamic fluid viscosity in the create fields.h. Next, in create fields.h, we initialize the basic kinematic colliding cloud that includes particle-particle interactions. Then we customize the Pimple LPT foam.c. For some customizations, we add the basic kinematic colliding cloud.h and read gravitational acceleration.h to the existing header files at the highlighted locations. Then we add the kinematic cloud.evolve function after the pimple corrector loop. And then in the u equation.h, we expand the momentum equation for two-way coupled system to include the feedback force effect on the fluid by the particles. This implementation is almost done, but we need some customizations within the make directory of the intermediate library in order to compile everything correctly. What we do is in the intermediate make files, we add the following line at the end, which is shown on the right hand side. Next, we tell the solver where it can find the intermediate library by opening and appending the highlighted lines in the make options file in the solver directory. Next, we name our Eulerian-Lagrangian solver in the make files in the solver directory and compile it using wmakeall. So once this solver is set up, what we do is we apply a certain boundary condition for turbulence known as turbulent DFSEM inlet. So turbulent DFSEM inlet is a synthesized eddy-based velocity inlet boundary condition to generate synthetic turbulence alike time series from a given set of turbulence statistics. At the entrance, a zero pressure gradient and fully developed turbulent flow profile are applied with Reynolds stress, length scale, and velocity scale obtained from DNS data by Moser et al. Okay. Corresponding to RE-tau 395. Implementing this method in LES improves simulations, reducing hydrodynamic development lengths and near inlet pressure fluctuations, thereby minimizing the computational resource requirements as suggested by Poletto et al. In 2013. So synthetic eddies, each representing a set of velocity fluctuations, are convected through a box surrounding the inlet plane, guided by the local imposed mean velocity. Upon exiting the box, these eddies are regenerated at a random location on the inlet plane. So on the right hand side, you see this inlet boundary condition that is placed in the 0 folder inside the U file. So this boundary condition is applied, and turbulence is synthetically generated inside the domain. Next comes the TKE budget equation. So here on the left hand side, we have turbulent kinetic energy, and on the right hand side, we have different terms that are contributing to that turbulent kinetic energy. So here CK is the convection term, PK is the production term, TK is the turbulent transport term, DK is the diffusion term, turbulent diffusion term, epsilon K is the viscous dissipation, and pi K is the pressure transport term, and WFP is the energy contributed by the particles on the fluid uh, when the particles are present. If the particles are not present, this WFP term is 0. So we can see that all these terms consist of fluctuational terms, and these fluctuation terms are calculated during the runtime by taking into account the variables that are dumped by OpenFOAM during the runtime. The variables that are dumped by the OpenFOAM are U, instantaneous velocity, and U mean, that is the mean velocity. And taking the difference, we can calculate the fluctuational terms, fluctuation velocities, and we can calculate this from that information. Next, we come to the validation. So after the solver is created, after the boundary condition has been applied, and the turbulent TKE terms have been set up, what we do is we run the simulation and we extract the results. So this is the particle Laden velocity statistics in a straight channel under the turbulent regime at a friction Reynolds number of 395. We found an excellent agreement of our model prediction with that reported in the literature. And this is the turbulent kinetic energy budget in the straight channels under the turbulent regime. Here, 4 different terms have been validated. Other 2 were negligible, hence not shown. So here also we found an excellent agreement of our model prediction with that reported in the literature. Now we come to some of the results of the model, my work, which I did in my PhD. So before going to the results, I'll briefly describe the problem. We have taken a straight channel and bent it at the middle by an angle of inclination theta in the streamwise with respect to the streamwise direction, and we applied at the inlet a fully developed turbulent flow profile where the length scale, velocity scale, and the Reynolds stresses have been extracted from DNS data of Moser et al., similar to turbulent DFSEM inlet boundary condition. And we also applied a zero pressure gradient. At the outlet, there was a fixed zero pressure boundary condition and a zero velocity gradient boundary condition. At the walls, no slip conditions were imposed, and periodic boundary conditions were applied in the spanwise direction. Now, to analyze the results, what we did, we divided our channel into 3 different sections. So the first section is the chi equals to 0.25 as shown here, as shown on the left hand side. So chi equals to 0.25 represents the straight section, chi equals to 0.5 represents the middle section, and chi equals to 0.75 represents the inclined section. We calculated the mean velocity profile of the turbulent flow at these 3 sections, and from that we calculated the slope and intercept of the profile in the turbulent core to obtain one Kármán constant and additive constant. So we plotted this for different angle of inclinations.
Abhishek, could you please summarize your results now?
Yes, sir. Yes, sir. So maximum variation in K and B was found to be at the middle section. Influence of increasing bend angle on K is weak and B marginally increased in the inclined section. So the TKE budget terms remain unchanged regardless of the changes in the angle of inclination of the bend in the straight section. Production and dissipation energies were of the same order, and loading the channel with the particles, the production term and dissipation terms were attenuated as compared to the particle-free case. And attenuation is followed by particle-fluid interaction term, assuming a constant value in the straight section, which indicates that particle extracts energy from the TKE. So that is it. Thank you.
All right. Thank you, Abhishek. I think this was very insightful. Again, showing how to modify the existing solvers. And like the previous talks, I request the audience to put down the questions or queries in the chat box. And I request Abhishek to see through the chats and reply to any questions if there is. Thanks, Abhishek. So we will move forward to our next talk. And the next talk is by Mr. Paras Singh from Delhi Technological University. And he worked as an intern with me. So Paras, please go ahead and share your screen to start your presentation.
Hi, sir. Am I audible?
Yes, we can see you and hear you. Please share your screen. Yes, we can see your presentation. Please go ahead.
Okay. Yeah. So, hi everyone. I am Paras Singh, and I'm a final year undergraduate student at Delhi Technological University. And today I'll be presenting our ongoing work at the BioFSI lab of University of Birmingham, aimed at investigating the impact of avian feather-inspired flexible flaps on the aerodynamics of airfoils at low Reynolds numbers. And this work has been done under the supervision of Dr. Chandan Bose. So, yeah, let's start. Yeah, to give you some perspective on the research background. So a bird wing is divided into two segments. The first one consists of these longer elements called the primary feathers, which help the birds to maneuver while takeoff, landing, or while cruising as well. And these shorter elements are the coverts, which help the bird in mitigating stall and perform high angle of attack maneuvers while catching prey or during gust conditions. Similar to the previous slide, so I've attached another image showing the coverts, but this time these coverts are present on the other side of the wing. And from this, I just want to put across the idea that the coverts can be located at either the pressure side or the suction side of a bird wing. Yeah, before discussing our work, I'll be just quickly pointing out some contributions to this area. So first one is aimed at studying the necessary parameters governing the flaps on the airfoil. So generally, the previous studies have focused on analyzing the impact of stiffness, mass ratio, length, and the position of the flap along the airfoil cord. And the second work is mainly concerned around the analyzing of impact of the flaps on the stall behavior. So it presents a qualitative as well as quantitative analysis of the influence of flaps. And finally, there are some works related to studying the influence of both pressure and suction flaps attached to the airfoil. And also, majorly, all these studies have been focusing on analyzing rigid flaps that are attached using a torsional spring on the airfoil. But in our study, we want to analyze the impact of flap deformation as well and its interaction with the incoming flow. So for this study, we'll be focusing on a simpler representation of this complex system. So what we are doing is we are taking a cross section of the wing geometry and modeling it as a airfoil with a rectangular flap attached to it. So as I already told, this flap can be located at the pressure or the suction side of the airfoil. But in our study, we'll be just focusing on the flap located on the towards the suction side. And the flap position along the cord is presented by x sub s, and its angle with the airfoil is presented by beta sub s. But in our study, we have fixed the angle as 90 degrees, as these are just primary investigations. And this slide presents the governing equations for both the fluid solver and the structural solver. And for our simulations, we have kept the Reynolds number fixed at 1000, and material properties of the flap are given, the non-dimensional material properties are given by K sub B, which is the stiffness, and mu, which is the mass ratio. And this slide presents the schemes as well as the solver for the fluid case. And we have tried to use second order schemes for the fluid case, and we have selected the solver accordingly, ensuring that the that the solver gives convergence as well as stability to our solution. Now, this slide presents the main coupling, fluid structure coupling framework that we have used. For the fluid solver, we have used OpenFOAM, which utilizes pimple foam solver, and the mesh morphing is being done using the quadratic inverse distance diffusion method. And this method was selected based on the mesh geometry created after the deformation. And this diffusion method was provide the best possible deformation of the mesh without giving errors like the negative cell volume error, etc. And for the structural solver, we use Calculix, which is again an open source solver, and it uses the implicit classical Newmark method with the spool solver. And both these solvers have been coupled using the open source library Precise, which uses the parallel implicit scheme with IQ and ILS acceleration. And this is a strong coupling method. And since we all know, OpenFOAM is a finite volume method which solves for the solution at the cell centers, and the Calculix is the FEM method, which is which calculates the solution at the node. So we need some data mapping scheme to facilitate the information exchange at the boundaries of both these bodies. So for that, Precise user provides us several data mapping schemes, and we have used the RBF thin plate spline mapping method because it's second order and provides us with greater flexibility for coupling compared to the other available schemes out there. And for the coupling time step size, we have chosen a time step of 1e minus 3 seconds after ensuring the time step independence test and mesh independence test. And this slide presents the flowchart of the information and data exchange between both these solvers. So I'll just try to simply explain it. So what happens is, since this is a parallel implicit method, we can start with either of the solver. Let's say we start with fluid solver, that is OpenFOAM. So it will start with the solution, and it will iterate till the required residuals are met, and then the quantity of interest from the fluid solver, in our case that's the force, will be exchanged with Precise, which will then send it to the solid solver, that is Calculix. So the solid solver will receive its boundary conditions uh, from the fluid solver through Precise and iterate till the required iterations are met, and this information exchange will keep going on. So with this strong coupling method, what happens is both these solvers they iterate till their residuals, but also the coupling we use several coupling iterations so that the coupling residuals also reach a desired set limit. That helps in stabilizing highly nonlinear cases. In our case also, since the deformations and the interactions are quite prominent, that's why we have chosen a strongly coupled method. Yeah. Now coming on to the some of the preliminary results of our simulation. First, I'll be presenting the results for single flap cases. In this case, the flap is located at x equal to 0.1 c from the leading edge of the airfoil, and the deflection envelope are presented as well as the histories of tip displacement along downstream direction and perpendicular to the airfoil. So it is evident that the deflections are in the downstream direction are uh, restricted towards only one side of the airfoil. And these simulations have been done at a mass ratio of 0.05 and mass ratio of 50 and stiffness of 0.05. Next are the results for single flap at x equal to 0.5 c. Again, uh, the deflection envelope is presented, and it's clearly evident that the amplitude of deflections are quite higher as compared to the previous case, and the LCO oscillations are reached after around 20 seconds. And in this case also, we get symmetric oscillations about the mean position towards both the upstream and downstream direction. And finally, for single flap, the flap location is at 0.9 c, and here also the deflections are restricted to both the upstream and downstream direction, and the underlying physics responsible for it will be discussed in the later slides. And here I presented the bar density of the oscillations of the flap, and it's evident that the flap location of 0.1 c gives the maximum frequency, whereas the flap located at the middle presents the highest amplitude of the deflections. the flow field of the 0.9C flap case is presented over here, and the interactions between the trailing edge and the vortices shed from the flap is evident from here, and also the vortices that are being shed from the flap are interacting with the shear layer from the leading edge, and the shear layer is getting split into the leading edge vortex and interacting with the trailing edge and the vortex shed from the flap. And these interactions are also evident from the vorticity contours. The previous ones were the LIC plots.
Paras,
And
please
these.
summarize your results. Yes.
Just a second.
I mean, please conclude.
Yeah. So I'll just conclude the single flap cases for now. So the statistics for the lift and drag coefficient are presented over here. And it's clearly evident that the 0.9C case gives a higher value of lift coefficient in comparison to the other flap locations, as well as the clean airfoil case without any flap. And also we can see that the 0.1C flap case gives the lowest possible lift coefficient, but at the penalty of the highest possible drag in this case. And I also have some results for the dual flap cases and the 3 flap cases, uh, which I'll not summarize over here. But the general observation is that for a 90-degree flap angle case, the single flap case gives higher statistics compared to the 2 flap and the 3 flap cases. Yeah.
Thank you. Thanks, Paras. Very nice talk. So please try to see the chat. If there are any questions regarding your presentation, please try to answer them. Okay.
Yeah.
Okay. Okay, so let's go ahead with our next presenter. And I actually request Mr. Rahul Sundar from IIT Madras, and he will be speaking on the overview of efforts extending OpenFOAM along the frontiers of scientific machine learning. Rahul, if you are here, please. Yes, Rahul is here. So please, we can see you. Please turn on your mic and share your screen for the
Am I audible?
presentation. Yes, we can see you and hear you.
Okay, great.
So Rahul is a PhD scholar in the IIT Madras, and he's working with Professor Sunetra Sarkar. Yes, please go ahead. Thank you.
Okay. Yeah. Hello, everyone. And I thank the organizers for giving me this opportunity. And I think this is a great venue to let people be aware of what kind of efforts are ongoing in terms of coupling OpenFOAM with the tools of scientific machine learning. And so I would like to say that science and AI are two sides of a coin, because now let's look at some. Okay, before I go, this is the outline of my talk. I'll just go into the background motivation behind scientific machine learning, its relevance, then what are the efforts, and also I'll discuss some perspectives and further scope of work that can be done. So why do I say science and AI are two sides of a coin? Now let's look at this. So this is a work that was done in 2021 where they had a complete digital twin model built of a heart. Now, however, this was completely mathematical model driven. So it had proper constitutive laws based on some assumptions. Now, what do we need is we need patient specific customization, diagnosis, or prognosis. Now, this can be achieved if we were to collect some real-time data from the patients itself or some historical data that's available. And how do we merge the existing models with data? This is where scientific machine learning comes into play. And another interesting and very critical application is a digital twin of the Earth. So how do we mitigate climate change is the biggest question right now. And how do we build models that are quite accurate in terms of their forecasts, right? So NVIDIA has come up with this project called Earth 2, where they're trying to build a complete digital twin of the Earth. So now let's look at what scientific machine learning is and always has been. It's about observation guided modeling. And trust me when I say this, it's not a new paradigm because it's been existing since the 1900s. And the only difference versus then and now is that you have larger scale of data, memory, and compute, and heavy advancements in the algorithms, hardware, and software. So now if you were to look at what it comprises of, it mainly comprises of a set of forward problems or inverse problems. So what do they mean is that, let's say you have an idea about what the system is, its physical laws. Then from there, you can move all the way to collecting data or getting your observations. And the reverse is what is called an inverse problem. And there are some very nice review papers on physics informed machine learning, scientific machine learning, which you can also look at by these authors. And now let's look at what a learning machine typically is, like a machine learning algorithm is. So you have an input vector that comes from some sample generator, right? This could be your initial condition, boundary condition, or some system parameter like the stiffness of your spring for an aeroelastic system. And then the system, when I say, is basically the fluid solid coupled system. And you simulate, you get your results, or you run an experiment and you get your results. And the learning machine does a particular task. Now, what this task depends on, which side of the problem are you in? Do you want some kind of a forward problem to be solved or inverse problem to be solved? So typical inverse problems involve, let's say if you want to optimize the shape of an aerofoil, then that is design optimization. And your learning machine appropriately has an objective that it needs to minimize in order to satisfy this problem. Or you have predictive modeling, like I mentioned about the Earth's digital twin. Or you have some missing physics. Let's say you have only partial observables from experiments like velocity data, but you want to recover pressure, you want to recover temperature, or you want to recover a constitutive law from the observables. Then it's called missing physics modeling. And a very interesting application is your automated physics discovery, where what you want to do is you want to run experiments on your aeroelastic system, but with an objective. And the objective could be, okay, I want to investigate which possible parameter combinations give me chaotic dynamics, or which possible parameter combinations give me highest lift, or which parameter combination gives me highest thrust, etc. Right? And there are some typical SciML applications in terms of optimal control, some sort of medical imaging, automated discovery, and forecasting, like I mentioned. So while there are many efforts to extend OpenFOAM for SciML, I would like to consolidate all of them together and put them under 3 categories. So I'll come to them one by one. So before that, we also saw in Mr. Shubham's session, where there are typically general Python integrations with OpenFOAM, like the PyFOAM, PyFlu, PyBind11 form, and Python PAL4 form, right? But however, we want some higher level abstractions where we want to couple OpenFOAM with some existing ML libraries and carry out the tasks that I mentioned earlier. So there are 3 categories. The first one is the closed loop category, where let's say you have OpenFOAM and an ML library, and you want them to be tightly coupled, where there are constraints, target variables, and feedback signals that go from OpenFOAM all the way to ML library, and reverse, where you have the ML library performs some computations on your model or the learning machine that I told about, makes changes in your solver controls or your input variables, or adjusts your parameters, and also provides some feedback signals to your OpenFOAM. And this is tightly coupled, and this happens in a synchronous manner. And this is what I called as closed loop. And mind you that this exchange of information or these feedbacks can happen either in memory or through file input-output operations, where you write files and then the ML library reads from the files. But what is more tightly coupled and efficient is where you have in-memory exchange. And type 2 is where you have a similar kind of a setup. It is bidirectional, but it need not happen synchronously. So you can have updates that are coming from OpenFOAM more frequently, or ML library updates coming more frequently. And here you don't have feedbacks as such. It is more loosely coupled. And you have in-memory again, or file input-output operations. In the final category is the post-hoc kind of coupling or integration, where you have OpenFOAM, the ML library, and the exchange happens only through file input output. There is no feedback as such. Only the target variables, constraints, or the input variable changes or changes in solver controls go from one or the other. Now, mind you, this whatever classification I told you is applicable for not just OpenFOAM, but any legacy HPC codes that you have also. And the frameworks that I'm going to talk about, some of them are directly applicable for your legacy HPC code. So you do not really depend only on OpenFOAM in that case. I hope it's clear until now. Moving on. Now let's look at the entire ecosystem that's available. So it's quite dense, as you see. So you have SmartSim, which is by a group from the HP Hewlett-Packard Enterprise, where they have open source the framework called SmartSim, which can help you couple your HPC codes with an ML library, any ML library for that matter. And typical ML libraries are your PyTorch, TensorFlow, and many others, but most commonly used ones are the PyTorch and TensorFlow, which provide a feature called automatic differentiation. I will not go into the details of it, and these details would be available in classical ML literature, deep learning literature. And there is something called automated experimentation, which is by Meta, and the library is called Axe. Again, it's Python oriented. So you see that your typical HPC codes are either in Fortran, C, C++, whereas all the ML libraries that you see have evolved in the Python ecosystem. So the reason why I'm saying extending OpenFOAM for SciML is because the maturity of these ML libraries is very high. They have been there for almost more than a decade, but these extensions or couplings with OpenFOAM have not yet matured, and they're still in their nascent stage. And we want OpenFOAM to adapt or adopt some of the features of these frameworks. This is why it is extending OpenFOAM for SciML and not vice versa. Right, so you have the libtorch, which is a C++ API for PyTorch, which has been coupled with OpenFOAM. And then another work by Romit Malik was coupling TensorFlow with OpenFOAM for turbulence closure modeling. And the FluidFOAM package, which is again falls under post hoc approach, where you have these FluidFOAM package mostly for post processing or any further analysis that you want to carry out on your OpenFOAM solver generated data. So now I'll look at the overall ecosystem, right? Like type 1, type 2, type 3. So I would like to talk about the open source communities that have been working in this area. So what I mean by SIG is a special interest group. I'll come to that. I'll leave it as a surprise for you all. And non-SIG contributions are mainly the SmartSim, which came from Hewlett-Packard, which is type 1 and type 2 kind of an integration. TensorFlow is a type 2 integration because you have a trained model, then you bring it into your OpenFOAM framework, and then use the model to infer any of the variables that are of interest. Then you have TorchFOAM, which is again type 3, which is more post hoc kind of analysis where you want to couple OpenFOAM solver generated data with PyTorch. And then GIMPrecise, like you would have seen in the earlier talk as well, where Paras had shown that he had used Precise to couple the fluid and solid solvers. So here what has been done is the solver is the fluid, and you have another adapter for reinforcement learning based active flow control. So this is another way you can achieve coupling. So Precise is one kind of a framework which allows you to do that. So they have coupled the Python based framework with the OpenFOAM C++ based framework. And the SIG contribution, that is the special interest group contribution, is the DRL form, which is again a library to implement active flow control, which is both type 1 and type 2. You can do it asynchronously or asynchronously. OpenFOAM SmartSim is where we have extended OpenFOAM to adapt features from SmartSim, couple them, and use SmartSim's capabilities within OpenFOAM. And MLFOAM or OpenFOAM ML Hackathon is a repository of all educational material and hackathon contributions from previous years on the SIG website. I'll give you a link to that as well towards the end. So we'll look at just the type 1 and type 2 closed loop ecosystem, which is the OpenFOAM plus SmartSim, which is very interesting and which is what would be very relevant for us moving forward as well. Which is, let's say, what SmartSim allows you to do. So this is your high performance code, C, C++, Fortran, or even could be Python as well, given Python's capabilities these days. So you need these ML libraries which can, produce some AI models, work with different data sources, and you have some code snippets as well. And they work on often heterogeneous architectures. What I mean by heterogeneous architectures, they can work on a combination of CPU, GPU, or just CPU or GPU. Right. So what this does, what SmartSim does is it allows in memory, no read writes to file system, all in memory communications of feedback signals as well as data through this framework called Smart Redis. the arrays are directly transferred from your HPC code to your ML library without having to rely on file transfers, which is, if you come to think of it, this is quite powerful because you can have these codes running synchronously. And this is very useful if you were to run automated experiments, if you were to build digital twins, or if you were to build active flow control of your flow systems, or any multi-physics system for that matter. So the paper by Tomislav Marek and others, they actually demonstrate this OpenFOAM integration with SmartSim for different use cases. One is by automated experimentation and optimization, and then partitioned SVD. So you had seen modal analysis in one example earlier, like in a previous session. So what this does is this partitioned SVD happens not post hoc, but in memory and coupled with the solver. So it is part and parcel of the solver, and or can be added as a function object to your solver. And then you have a typical mesh motion algorithm like radial basis function or displacement Laplacian. What if you were to replace it with a neural network based mesh motion adhering to some constraints? So this is what was achieved using ANN based mesh motion algorithm as well. So this was demonstrated in this paper, and there is an open source repository available for people to try out the tutorials and to also contribute as well. So do check it out. And so coming to the general pros and cons of any of these frameworks, right? Like every kind of integration that we desire comes with its own pros and cons. So what we see is, as it becomes more tightly coupled, we have higher hardware level efficiency because you have everything happening in memory and everything is being utilized quite well, and you don't have any delays. You don't have latency. But what I mean by latency is that you're able to transfer data quickly, you get feedback signals quickly, and the iteration time per iteration on either of these ML or the OpenFOAM solver algorithms is lesser. Now, however, post hoc approach is highly flexible and easy to adopt because all you need is file input output operations, and you don't need to touch the OpenFOAM solvers, or you don't need to touch the existing ML libraries. All you need to do is choose what application you want to work on, try to just integrate them through the file input output operations. All that you need to take care of is the file format. Then the final one is that you see that to achieve a tight integration, it's a high development effort problem. And because most of these, let's say even SmartSim was actually open sourced by a big corporation, which was the Hewlett-Packard, and it required a big team to even build such a framework for people to use with a lot of features available. So this requires a higher technical development effort. So I have also listed some general cons and pros of these frameworks. Like main issue we see is we don't have too many standardized frameworks available. And even if they are available, they're not under active maintenance. So they're not updated to the current version of OpenFOAM or current version of OpenFOAM ML libraries. And you don't have, the reason is you don't have full-time developers available to implement these open source projects that do for free. And we don't have enough awareness amongst users nowadays about what frameworks are available that we can quickly contribute and build upon. One other reason is that they need to be quite well documented, more readable with tutorials for early or easy adoption. And you need higher level abstractions on top of very code intensive frameworks. And the general pros is that since the field is still nascent, although I have mentioned about these problems, field is still nascent, a lot of scope ahead. You have already seen how dense the ecosystem has become over just a couple of years. And through hackathons, workshops, trainings like this, you could achieve active and intense development of some features over a short time. So some perspectives are that you need more of open source. Bottom line is that like you need more of open source so that you have decentralized novel contributions coming from any part of the world and from anyone who is passionate about this field. And the outcomes of that is that you have, yeah. I'm done. Yeah. And closing, I would say I would like to motivate you all to show where we are right now and how do we get to where we want to be. So we know we are here. We have function approximators, we have pattern recognizers with machine learning and deep learning. But artificial intelligence is where we want to get, where we augment our decision making with AI, and where you have automated planning, reasoning, cognition, and execution. And how do we get there? Is again through open source and building, quickly experimenting, implementing variety of ideas and benchmarking them and standardizing them. So I'd like to lastly close with this, where we have an OpenFOAM data-driven modeling special interest group, which is part of the OpenFOAM data committee. We mainly focus on improving the awareness of SciML plus OpenFOAM, organize workshops and hackathons. And this happens half yearly. So I have the QR codes for the wiki page and the GitHub repositories. So if people are interested, you could just scan, then visit them and look at them. And the SIG is chaired by Andre Weiner and Tomislav Marek, who are very active in organizing these workshops and hackathons. Finally, thank you, and I would like to leave the floor for some questions if any.
Thank you, Rahul. Very, very interesting talk and very futuristic. I think it will be very much helpful to the audience. So, like the other talks, I again request you to look through the chat. If there are any particular question, please answer them. And we will be closing this session now for lunch. And we will come back at 2 p.m. with our training session 2. Thank you all for being with us. So please join us again at 2 p.m. for the training session 2.
Okay. So I have a couple of questions in the chat.
Yes, Rahul, you can just answer them in the chat.
Yeah.
You don't need
So
to answer.
So Asma has a question about good source to start digital twinning as a beginner. I would say OpenFOAM plus SmartSim is a very good start. And you can find, if you can scan this QR code, you will be directly led to the GitHub page where you can find the repository for OpenFOAM plus SmartSim. And if you have any issues trying to run those tutorials, you can certainly get in touch with me. And for the presentation, okay, Aditya asked about something which is more general. Presentation, of course, I've used PowerPoint. And for the flowcharts, I use draw.io. Draw.io is again free and free to use, and you can make really nice LaTeX compatible flowcharts with that. And yes, so you want to do supervised, unsupervised, or semi-supervised learning. Since it's all dependent on your ML library, the kind of functions that you call from it, you can carry out any sort of task. It just depends on, it finally boils down to how you want to structure your task, right? So what's your input, what's your output, what do you want the machine to in fact learn? And I hope that this gave a very high level overview of the ecosystem. And once again, thanks for the opportunity. Hope to be
Thank you,
engaged
Rahul.
in a
We really enjoyed it.
Thank
you. So we are closing the session now, as I said, and you will get a feedback from, probably it has been already shared with all the registered participants. Please fill the feedback form, and it is a must to get the link for the recording and the certificate for participation. So please fill out the feedback form to get the participation certificate and also the link of the recording. So please join us at 2 p.m. because the next speaker for the training session 2 is joining us from Japan. So there is a time difference. So please join